Good morning, good afternoon, and good evening, everyone. Thank you for joining our first webinar of 2023. Today's topic is one which has been attracting more and more attention: PFAS and how pyrolysis and biochar can help. Perfluoroalkyl substances, I had to look up how to say that. It's easier to pronounce PFAS, are a man-made class of chemicals that lead to serious health issues such as various cancers, reproductive impacts, hormone disruptions, and more. PFAS has been manufactured for decades, and it is now found everywhere in our closets, our kitchens, our rivers, air, and soils. And it's often referred to as a forever chemical due to its high resistance to degradation. But we're finding that pyrolysis and biochar are pointing the way to forever no more. There are a growing number of thermochemical technologies that are showing that high heat and low oxygen environments can substantially help mitigate PFAS in organic materials, and that the biochar can help capture PFAS in wastewater. One of our speakers today, Paul Nielsen, and I were chatting about this last November at COP27, and I immediately wanted him to tell us all more about the underlying science and about some of the commercial opportunities they're seeing. So, to tell us more about the underlying science about PFAS degradation and capture, we will first hear from Dr. Gerard Nielsen of the Norwegian Geotechnical Institute, and he's a professor at the Norwegian University of Life Sciences. Gerard is exceedingly well published and well traveled when it comes to biochar, and most recently he's been working with VOW on carbonizing sludge, digestate, and other potentially tainted organic materials. After Gerard, we will hear from Paul Nielsen, the VP of Innovation for VOW, and he will discuss some of the commercial opportunities for PFAS mitigation. When Paul's done, we'll have a Q&A session, and just another reminder, this is being recorded and the links will be sent out sometime next week. So Gerard, are you ready to go?
Absolutely. Thank you very much for introducing me and inviting us to talk about biochar in PFAS mitigation. It's something we very much like to talk about. So welcome to you all. Thanks for your attendance. This is my presentation. As Kathleen already said, I'm at the Norwegian Geotechnical Institute, NGI, and Norwegian University of Life Sciences. Working together with my PhD student Erlend Surmu, master students Clara Lade and Katinka Kraan, Paul Jaren Nielsen, our main technology man that you will hear later on, Nicolas Hageman of the Ithaca Institute, close collaborator to Hans-Peter Schmid, that many of you know, Gabriele Castra, who is kind of the best PFAS analytical chemist in Norway, Hans-Peter Arp, who's leading the sludge effect project that I will tell you more about. But the charming thing is here to make biochar from PFAS contaminated sludge and then use that biochar to mitigate the risk of other PFAS contaminated matrices, such as water and soil and even sludge. Our hypothesis is that biochar could turn polluted waste streams into clean resources. How does that work? For example, we have waste timber that can be lightly contaminated. We can have food waste, and the most interesting topic for tonight, sewage sludge. We pyrolyze that into biochar, and then we use the biochar, we mix it into the soil where it binds contaminants so strongly that they're not available for uptake in plants or animals anymore. So the beneficial thing is that these organic waste fractions can be contaminated by microplastics, by organic compounds, including these ubiquitous PFAS, and by metals. And what happens then ideally is that you sequester the carbon, as we all know and we all like with biochar. We destroy the plastics and the PFAS, and we immobilize the metals. That's the ideal thing. So now in practice. A lot of organic waste in Norway. It will not be different in the US. Only you can multiply the numbers by 100 probably, because we only have 5.5 million inhabitants. Waste timber, as I said, one of them, surprisingly much, 660,000 tons per year for only 5.5 million people. Garden waste, we got a lot. Forestry residues, even more, but more or less clean. Food and biological waste, 340,000 tons per year, also including both plastic, pharmaceuticals, PFAS. Same is true for sewage sludge, of which we got 200,000 tons per year, and that is getting more and more problematic once we find out how problematic these PFAS compounds are. I will show you how problematic that actually is to spread sewage sludge on your agricultural soil. You should definitely not be doing that. It's not a good idea. This is the project that we got, the VOW project, which stands for Valorization of Organic Waste, VOW. So inspiring that Paul's company was called after the project acronym. That's great. And we then want to make that organic waste into sustainable products, biochar products for cleanup of contaminated water, soil, and air. So plenty of partners, even one American partner, University of Florida, that's Andy Zimmerman in Gainesville. I want to mention the Technical University of Denmark, top one in the world when it comes to LCA. They will do an LCA of these pyrolysis treatment as an alternative treatment to regular practice for these various organic waste fractions: garden waste, waste timber, sewage sludge, and food waste. Subjected to pyrolysis, then you get biochar, syngas, and bio-oil. Nothing new for most of you, I think. The biochar then you can use for water and air treatment, for treatment of contaminated soil, soil improvement and climate change mitigation, and also treatment of waste before landfilling it. The syngas you can use for heating and for obtaining biogas. The main focus of this talk and of our project is then the sewage sludge pyrolysis, biochar, water and air treatment value chain. I will have to give you a little crash course on PFAS, 5 minutes. I'm teaching in the subject, so it's very nice to share that knowledge. These so-called forever chemicals, what is so bad about them, and why are they such a big threat to our food and drinking water? This is general structure for the non-chemists of you. This is carbons are at these intersections, so it's 1 to 8 carbons. This is an 8-carbon carbon chain. All the hydrogens have been replaced by fluorines. That's why you call it perfluorated. That means totally fluorinated. And then you have this sulfonic acid head group. So basically all these PFAS compounds, which is the joint name for all these compounds, they have a hydrophilic head group and then a tail which mostly consists of carbons and fluorines. Here is also a picture of the Oslo Airport firefighting training area, because firefighting foams, especially the old ones, it's now forbidden. They're a big source of especially PFAS, but also many of these other compounds. What is very nasty about them is that they are persistent, because this carbon-fluorine bond is the strongest bond in organic chemistry, and it's very strange to the bacteria that can degrade many organic compounds, so it's almost impossible to degrade. It's almost like plastic. It will stay for hundreds of years in the environment. They're very mobile in contrast to many of these classic organic contaminants. They can spread very quickly to recipients, and they are surprisingly toxic, as I will come back to. So remember that name, PMT chemicals. It will maybe surprise you that there is a whopping 5,000 different of these compounds that we have emitted into the environment. And that's a terrible mountain to climb in a way, to regulate and to even measure, because only 56 of them are regularly analyzed. What happened to the other 4,944 is pretty unclear. What we do know is that many of them are degraded because they can be degraded somewhat, but then they often end up as PFAS or related shorter chain compounds. So this is one of the kind of end products that are so persistent that they will be there forever for foreseeable periods. But many of these 5,000 compounds will actually be degraded somewhat, and it will end up as PFAS. So you see often that the PFAS dominates. The scary thing is, about this is that only 4 of these PFAS compounds, 4 out of 5,000, are properly regulated. And then properly, we'll see about that. So as I said, using firefighting foams, surface coatings, very handy if you have this paper cups and paper plates. It's very handy with a PFAS coating, only that this stuff is so toxic. Personal care products, building materials, clothing, especially all-weather clothing, very ideal that it repels both water and stains. But then again, it's so toxic. Ski wax, a very important use in this beautiful country where everybody loves Nordic skiing. So many of you have probably seen this film, Dark Waters. It's about PFOA, which is a compound that's very similar to this PFOS I just shown, only with an acid head group, but also with 8 of these carbon groups. If you haven't seen it, see it. It's pretty scary. But we, as environmental chemists, including me, we never thought it was so bad with PFAS. That's why it got regulated so late and so little. The main reason is that the effects are so subtle. It's subtle chronic effects, mainly of hormone disruptions. For example, change in sex of alligators in the Everglades is probably explained by PFAS. But it's very hard to quantify such subtle effects. Usually we do some acute tests in water if we want to measure the toxicity of a compound. And yeah, then PFAS is not so bad. So we never thought it was so toxic on the long chronic term. But it's probably the main reason that there's hormone disruption, a severe reduction of human fertility. Yeah, we can discuss how bad that actually is, but probably PFAS is the cause. To sketch that mounting knowledge on it, in 2013, so it's not even so long ago, the tolerable daily intake of only PFOS, this one compound of the 5,000, was 150 nanograms per kilogram body weight. Already in 2018, that was corrected to a tolerable weekly intake of only 13 nanograms per kilogram for just still PFOS, so 10 times more strict. And then in 2020, it was even reduced further to 4.4 nanograms per kilogram body weight. So that's a part per trillion. It's very little, in fact, nanogram per kilogram, 10 to the power 12. And that's for the sum of 4 different compounds. So then it was even down more, as you see in this graph, from 2013 to 2018 to 2020. Came down a lot because we discovered the toxicity of these compounds was actually much, much higher than we initially thought. Number to remember, the soil quality guidelines in most countries that have guidelines for PFAS at all are in the order of 0.1 to 10 nanograms per gram soil. So that is part per billion, which is still pretty low. To sketch the crisis and how big this problem is, we have the serious PFAS crisis in my country of origin, the Netherlands. In 2018, this chronic toxicity was finally quantified. So then the regulators in the Netherlands got startled. They want to be best in the world to regulate such chemicals. So they set a toxicity-based upper limit for PFAS of 0.1 nanograms per gram for reuse of soil. But they never thought of that benchmark would be exceeded in every single building project. So in every project, they got a problem and they needed to stop because they needed to analyze and remediate PFAS. So the whole building sector stopped, and that made them block, in fact, government buildings. This is the middle of The Hague, the government say a site in the Netherlands. They're blocking everything, and yeah, they're just very angry because the whole building sector was coming to a grinding halt because of these PFASs. So yeah, that was not so much fun, of course. So then they temporarily eased those rules, not based on toxicity, but based on practice to 8 nanograms per gram. So that's a bit the background of these values. But remember that number, that 0.1 part per billion nanograms per gram is in fact problematic already. And if you want to regulate, you need to be around 10 parts per billion nanograms per gram, because these numbers are coming back in the presentation. So the important questions we were posing in the WOW project is, what is the fate of PFAS and also metals during pyrolysis? And can you use then sludge-based biochars for PFAS remediation to go down to these numbers? So then the idea is again, sewage sludge to biochar, PFAS destroyed, metals bound. You use it as a remediation agent, so it sorbs the PFAS, and then if you use it for wastewater treatment, you might be able to regenerate it, get out the PFAS again, and reuse as biochar. So what is a sorbent? Many of you have maybe not heard of that term. So that's a material that binds a contaminant very strongly. And usually activated carbon is used, but as you will see in this presentation, biochar can be at least as good as activated carbon. And yeah, then of course you have valorized basically a product with negative value if you make it from sewage sludge. And some current uses of sorbents is then in wastewater cleaning, landfill leachate from landfills, drinking water treatment, air filters, and then soil remediation. So how does that work for water cleaning? For example, you have these fluidized bed flow-through systems where you have below a membrane, you have an activated carbon or biochar slurry, and you have the water going in here, going through that fluidized bed, going through the membrane, and then much cleaner water is flowing out of the outlet. So that's one of the ideas that this biochar can be used for. In soil remediation, it looks like this, referring to the IBI white paper of already quite some years ago that I together with my colleague Sarah Hill wrote. Then you put the biochar into the soil and you get a transfer of your PFAS from your soil particles to your biochar particles. As I told you, the PFAS is very mobile in soil because it doesn't bind so strongly to soil particles, but it does bind strongly to biochar particles, of course, if you add the biochar for this purpose. So the idea is that the PFAS is bound so strongly to the biochar particles that yeah, hardly anything leaches anymore. And if it doesn't leach, it cannot be taken up by plants or animals because plants and animals, they can only take up through the water phase. So if the PFAS from the soil particles is to be taken up, or from the biochar particles is to be taken up by plants or animals, it has to go through the water phase. So if it doesn't get released from the biochar, it is not going into plants and animals and posing no risk anymore to the biota. That's the whole idea. Yeah, so then we pyrolyzed some of these sludge fractions. Paul will tell you much more about this technology, but very quickly, I have to take some principles before presenting the data. Pyrolysis up to 800 degrees. What is important to note also is that there was combustion of the syngas with propane between 700 and 900 degrees. And then we measured the PFAS and the metals, both in the biochar and what was coming out of the chimney. So the chimney is what was emitted here after combustion chamber with propane, and after the condenser where the syngas was condensed. Pyrolysis reactor electrically heated. So question 1A is then, does pyrolysis remove PFAS? First, of course, we had to analyze how much there was in the sewage sludges. So we found, not really surprisingly, that sewage sludge contains a lot of PFAS. Remember that 0.1 nanogram per gram number above which a soil is toxic. So here you see, for example, for digested sewage sludge number 1, 56, digested sewage sludge number 2, 441, lime sludge 340, and interestingly, a raw dewatered sludge from Oslo Airport watershed 214. So that's about 100 to 1,000 times higher than what can expect it to be toxic. This is the percentage of these various PFAS compounds that we identified. So sometimes there are 4 carbon, PFBA, butyric acid, is dominant. Sometimes the pentanoic is dominant with 5 carbons. Here, the 5 carbons also is dominant. It varies a bit. But there's a wide range of sources and a wide range of distribution patterns, and definitely not a good idea to put this directly on soil, as is current practice in many countries, I have to note. But the good thing is, if you pyrolyze that, there are some residual PFAS in biochars. Many people are claiming that they get rid completely of the PFAS, but then they don't analyze well enough, because it's quite difficult to analyze PFAS at these very low amounts. But as I said, we had the best lab in Norway on PFAS at the NTNU University in Trondheim. But more than 95% of the PFAS is gone. So that is really good news. If you look at this graph, this is again this part per billion nanograms per gram. You remember 0.1 is basically toxic, but benchmarks are usually around 10. And then you see they're all below that benchmark, at least, even when pyrolyzing only at 500 degrees, where most of them survive. But if you increase the temperature, more of these PFAS are gotten rid of. And at 800 degrees, you virtually have nothing anymore. So that's very good news for these 4 different sludge-based biochars. So 10 to 1,000 times lower PFAS, 60 to 100% fewer congeners, and 97% of this remaining PFAS is longer chain. The short chains are cracked, I should say, destroyed. That's good. So we are actually the first globally to quantify PFAS emissions through the chimney. And unfortunately, there is a tiny fraction of the PFAS that survives both the pyrolysis and the after combustion at 700 to 900 degrees. So here are again 3 of our sludge-based biochars, 3 different pyrolysis temperatures, and there we quantified the emission factors in milligram of PFAS per ton of biochar. So there you see it's quite all right for many cases. Here it is really low for the lime sludge at 600 degrees, but also the digested sludge at 600 degrees, there was still 3 milligrams per ton. And milligrams doesn't seem much, but if you know that nanograms per gram already is problematic, then it's not trivial to have these emissions. So you should do something about it. The fraction in the particles is variable, can be everything in particles, quite easy to remove with a scrubber, for example, or a filter, but in some cases also relatively little in the particles. So it's all in the gas phase and more difficult to catch. So 0.01 to 3 milligrams PFAS released per ton of biochar, strong variation with feedstock and temperature, and part of the emissions is particle-based, where a filter or scrubber will work. But we, of course, have an uncertainty around non-quantified degradation products. We quantified these 56 compounds, but as I told you, there's 5,000 of them, 4,900. Nobody in the world can analyze, and that's a worry. We do as best as we can, but we're not there yet, I should say. This is the mass balance for the PFAS, more than 95% degraded, as I said. This is these digested sludges. So you see decomposed is the green, 95.5%. About 3% is emitted and about 2% you'll find in the biochar. This is the best case, this digested sewage sludge at 700 degrees, 99.97% decomposed, 0.03% emitted, 0.00% in the biochar. That is what we want, of course, but don't always achieve. So we need to find out when do we achieve this, invariably this, and not this with the 3% emitted. Okay, so question 1A, yes, I think we can crack the PFAS, but we need to be careful. That's the answer. So question 1B is, does pyrolysis immobilize the metals? I will be a bit quick on that since we want to know about PFAS, not so much about metals. But still arsenic, I give a few examples. You have these European Biochar Certificate guidelines, these high and low values. So you see for arsenic, most of these sludge biochars are above the EBC low, but below the EBC high risk limit, a bit independent of temperature. What we did was then leaching tested ambient pH of the biochars, pH 8 to 9, and then we buffered it to pH 5 and pH 4 to see whether acidity, soil acidity would leach these metals out of the biochar if you would apply it to the soil. And then you see clearly 2 things basically. The leachable fraction is very little, it's less than 2%, even at 500 degrees. And if you elevate the temperature to 800 degrees, almost nothing is coming out, not even at pH 4. So that is really good news, I should say. Again, if your temperature is high enough, almost nothing of your arsenic, quite a toxic metal, will come out, even at pH 4. So that's good news with regard to the metals. Copper is another case. Too much copper in all these biochars, all above the EBC high risk limit, which is 100 milligrams per kilogram. But again, if you do leaching tests at low temperature, still about 1% is leached at these low pHs. But if your temperature is high enough, less than 0.1% will leach. Zinc, same picture, problematic with regard to the EBC guidelines, but if you do leaching tests, less than 10% will leach, so a bit more than for the other ones. But if the temperature is high enough, you zoom back at this 1% at ambient pH, maybe 0.1%. Yeah, so only a little bit will leach, and at high pyrolysis temperature, even a low pH doesn't matter. You will not get out these metals. So we did also emission factors for the metals. This is far too complicated table for a quick presentation. I apologize about that, but at least we have the numbers. They will soon be published. You either will probably, you see here that there is quite a lot of chromium and nickel and lead emitted. For example, this waste timber biochar at 800 degrees, then you get 138 milligrams of lead per ton. You don't want that in the environment. So you will need a scrubber or something to clean, or you will have a certain allowance of emission budgets if you do this on an industrial scale. But the good thing is 70 to 100% is retained in the biochar, and then we have shown that that part that is retained in the biochar is not so problematic, fortunately. So that's about the metals. Summing up, so especially copper and zinc are over the EBC values, but there's low leaching, even at pH 4, very low leaching after high temperature pyrolysis, and pyrolysis is a good way to render these metals less problematic. Okay, then the most exciting part, I should say, about the presentation and our findings is that yes, sludge-based biochars are good PFAS sorbents. I've worked in this field for about 20 years of strong binding of organic pollutants to highly sorbent carbonaceous particles, and even this surprised me as an absolute global expert in the area, I should say. So it's quite exciting results in all modesty. Talking to the USA, we don't have to be so modest. In Norway, you always have to be modest. I can tell you. Anyway, in water treatment, we tried, and there we then use these sewage sludge biochars as so-called sorbents. We had unactivated sewage sludge biochars made at 700 or 800 degrees centigrade. And then we did sorption tests or binding tests to the biochar with 6 different PFAS compounds. There was an excellent master student called Katinka Kran who did these experiments. She made simple systems with the biochar in water, shook that for 14 days, filtered that, and measured the PFAS in the eluate with these very advanced LC-MS analysis methods, again at that top university that we have in Trondheim. So what she saw for the first time actually is that sewage sludge biochars are better than wood-based biochars and almost equal in performance to commercial activated carbon, and that I should say is no less than sensational. Looking at sorption isotherms, you probably don't do that every day, so I'll guide you through a little bit. Here is the concentration in the water of these PFAS compounds. This is PFOA, this 8-carbon acid, the one that the whole Dark Waters documentary is about, and that was DuPont's biggest headache over there. Concentrations from 0.1 micrograms per liter, quite environmentally relevant concentration, I should say, 100 nanograms per liter, up to higher concentrations. And then you see that even at a concentration as low as 0.1 micrograms per liter, you already have a concentration on our biochar over 100,000 micrograms per kilogram. This is a logarithmic scale, logarithm of the concentration in the biochar between 5 and 6. So logarithm of 6 means 1 million micrograms per kilogram. So bottom line here is even at low water concentrations, you have enormous concentrations in your biochar, and you have an enormous effectiveness of removing those scary PFAS compounds from the water. but also a big variety between the various biochars. It's all expressed, this sorption strength, as the so-called K value. This is a logarithm, so a log of the K value of almost 6 means 1 million times higher concentration in the biochar than in the water. And here about 100,000 times higher. So still very good, but not as good. And you see here the clean wood chips, CWC biochar, 100,000 times higher concentration in the biochar than in the water. And if you compare that to these log K values as an expression for sorptive strength for activated carbon from the literature, from our group, in fact, then you see 5.6, 5.4, 300 to 400,000. It's in the same order of magnitude for these unactivated sludge biochars. And that's very exciting, I should say. We also did soil remediation experiments. There we added waste timber biochar, which was activated to 2 different soils, also from a firefighting area at another airport in Norway, Riga Airport. It's a regional airport where they have huge contamination problems with these PFAS compounds. There we had a low TOC soil, so very mineral soil with almost no organic carbon, and a very peaty high TOC soil with 34% organic carbon. We had various degrees of activation. And then the good news was that for this low TOC mineral soil, even 0.1% of our activated biochar reduced then the leaching by 76 to 92%. And if you add as much as 1% biochar and you activate your waste timber biochar, you remove almost everything. Much more difficult for the high TOC soil because there is much more competition from the soil and there's much more fouling of your biochar by the natural organic matter. It kind of competes with your PFAS for sorption sites on the biochar, and it also blocks the biochar from binding these PFAS effectively. So if you have a lot of organic carbon and a difficult soil, you might need 5% of very well activated biochar. Then you still get 99% effectiveness. But if you don't do that activation or you add too little biochar, you don't get this very good effectiveness, only 14% here, for example. So similar effect for the other PFASs. This is for PFOS, the most ubiquitous of these 5,000 PFAS compounds. Okay, last part of my presentation. Yeah, I still have some time, I see, so that should go fine. Our student Clara Lade, she did stabilization of PFAS contaminated soil with waste-based sludge biochar and measured transport in such column tests where we pack a column with soil and pump through water. And then see how much the PFAS is held back by the soil with biochar. So then, of course, we have a control soil with no biochar. Then we have this clean wood chips biochar. We have the digested sewage sludge char again. We have this dewatered raw sewage sludge again. We have the waste timber biochar, but unactivated. We have another digested sewage sludge biochar, and we have this activated waste timber biochar that was so fantastic in the previous slide. So we measured that then at 6 liquid to solid ratios, 0.1 to 5. So 0.1 means that you just take the first flush basically of the water coming from this soil, and then you keep on pumping. The elegant thing here, I feel, is that we had PFAS contaminated soil from the firefighting training area at Oslo Airport, but we also used the raw sewage sludge from the very same Oslo Airport, which is PFAS contaminated because of this contamination source. So it's in fact quite elegant that we use the sludge which is PFAS problematic because of the same problem to remediate the same soil, which is also from Oslo Airport. It's a very nice example of circularity, we feel. So again, 29 different PFAS we identified of the 56 we tried to measure. 88% was PFAS, so that also underscores PFAS is abundant in this firefighting foam, and also a lot of these bigger PFAS compounds are degraded to PFOS. So in the end, you often see a lot of PFAS, but you also see a lot of the other compounds. And here the total concentration in the soil was a whopping 1,333 nanogram per gram. Remember that 0.1 nanogram per gram being toxic in the Netherlands and everywhere else. So here you see the graphs for the PFAS in the leachate. This is the PFOS again, the most abundant one. Mind you, this is a logarithmic scale. So it goes from only 1 nanogram per milliliter to 10,000. And then you see clear differences between this control without biochar. Then you see again this clean wood chips biochar is not so effective. The unactivated waste timber biochar not so effective. Starts to get better with digested sewage sludge 1 and 2. Sorry for the wrong. This is 1. This is 2. The raw dewatered sludge from the very site was very effective. Again, this sludge number 3. You see it was a factor of 10 for each interval, so at least 100 times reduced. And then this activated biochar from the waste timber was the best. So this is non-logarithmic. For the other compounds, this is a C6 compound sulfonate, where you see from the control to the wood jars to the sludge jars. The sludge jars all fall in one line because the leaching is far, far less than from the control. So it's super effective even with 1% biochar in these soil columns. Also effective for this 6,2-FTS. It's another CF6 compound. There's a multitude of these buggers. So this bar diagram shows then the percent reduction in leaching compared to the control, of course. So you see the clean wood chips biochar and waste timber biochar not so good, less than 40% effectiveness. But you see these two of these sludge biochars and this activated waste timber biochar, almost 100% effectiveness for this most ubiquitous PFAS compound, the PFOS, the octanyl sulfonate, the C8 sulfonate. For the C6 sulfonates, you see slightly less effective, up to 80%, but still the same pattern, with these 3 being the best sorbents. Same again for the 6,2-FTS. But what I wanted to show you is this CF5 compound, CF5 acid. There you see the effectiveness is quite a big deal less, only 40% for these 2 sludge biochars. So if you want to do something about this compound, you need to add more biochar. But yeah, it all boils down to you need to know what compounds you are looking at and what benchmark do you want to achieve. But unfortunately, this is not even one of the regulated PFAS. So in practice, people will not worry enough about it. But for this other one, PFSOA, almost everything is gone, almost 100% reduction in leaching compared to the control. So basically, the longer the chain, the better the effect. That's no surprise regarding the sorption mechanism of biochar. Sludge jars are better than wood jars. That was an enormous surprise, but it can be explained, as I will show in the next slide. And this activated wood biochar was the best, made by the Ithaca Institute. Yes, what was very interesting is that we also looked at dissolved organic carbon leaching from the column and saw the same order in effectiveness. You see that this clean wood chips biochar and waste timber biochar are not so effective in reducing DOC leaching from the soil, but this activated biochar and these sludge biochars were much more effective. This implies 2 things. It can be used also for water cleaning for dissolved organic carbon, and that probably much of the leaching of these compounds of the PFAS compounds is happening by binding of the PFAS to the DOC. So it's very good to have this co-binding of DOC and PFAS to the biochar. Yeah, so this sums it up, the column experiments of our student Clara. Activated waste timber, 99.8% reduction of PFAS leaching. This raw dewatered sludge from the area, almost 99% with only 1% biochar addition. These digested sludges, also over 90% reduction in PFAS leaching, but the effect was much less for the clean wood chips biochar and the waste timber biochar, 30 and 40% approximately. So why were these sludge jars more effective than the wood jars? That surprised us, but not anymore, because we could explain it with the help of Andy Zimmerman at Florida University in Gainesville. He measured surface areas. At first, we got the surface area, which was much higher for the clean wood chips biochar than for the sludge biochar. So that puzzled us. But then we started to look at the pore size distribution in relation to the size of the PFAS compounds. So here you see the ultra nanopores. That is really small, below 1 nanometer, 1 nanometer 10 to the power minus 9 meter. So that's a thousandth of a millimeter. It's really the very narrowest pores. There you see that the wood jar has much higher pore volume, PV is pore volume in cubic centimeters per gram, than these two sludge jars. But if you look at the larger pores above 2 nanometers, between 2 and 30 nanometers, you see that this wood jar doesn't have so much additional porosity anymore in this size range. Whereas the raw sludge number 3 that sorbs so well still has a lot of porosity between 2 and 30 nanometers size. And then it turns out that these PFAS molecules, this is this PFOA, the DuPont problem molecule that our student Katinka did her master's on. It is 1.4 nanometers long and 0.6 nanometers wide, and you need then about 2 nanometer pores at least to accommodate this compound. Otherwise, it simply doesn't fit. So all these pores are very much represented in the wood jar, but they're worthless for PFAS binding. And it's these pores above 2 nanometers that very nicely accommodate the compounds of this size. So we think that quite elegantly explains why the wood jars were disappointing. So the wood jar pores were simply too narrow to accommodate these large PFAS molecules. So the overall conclusions very quickly. 95% of PFAS is decomposed during pyrolysis. Very good news. Some PFAS are emitted, less than 3%, but we still need to be careful if we do this in large scale. Metals are mainly immobilized, which is good news, but also there we should take a bit care for metal emissions. And sewage sludge biochars can be valorized as effective PFAS sorbents. There's no doubt about that. That's our big discovery, I should say. So the one project was this WOW project that I mentioned already, financed by the Norwegian Research Council in a joint industry sustainability call. The other project is led by my colleague Hans-Peter Arp. It's in this environmental research call of the Norwegian Research Council. So it's called sludge effects, and the idea is to remove hazardous substances in sludge and plastic waste through various types of thermal treatment. So incineration is also a part of that project. So this is the crew that made much possible. This is the Surmu guy that you saw many times, this fantastic PhD student. This is the guy you will hear speak next. That's Paul. Yeah, now the rest I won't introduce. This is our contact details of me and Erlen at NGI and NMBU. This is Erlen. This is me, project leader for the project. This is Hans-Peter leading the sludge effect project. And this is Paul that you will hear next. So just look forward to a very nice part 2 of this talk. And thank you very much for your attention. Much appreciated.
Thanks, Gerard. Paul, do you want to put your camera on and unmute?
There we are.
All right, thanks.
Try to share my screen. You can see my screen now?
Yes,
In presentation mode?
it is.
Okay. I have to prop it up. There we are. Sorry. I'm sorry. Give me a sec.
Anything we can help you with, Paul?
It's I just try to open this one. Let me see. Again. There we are.
There you
So,
go.
are we good? Sorry for that.
Yep.
Thank you for having me. My name is Paul Ere Nilsen, coming from WOW, where I'm an active part of the innovation team. We are doing the development and research for the pyrolysis in particular. WOW company, briefly, comes originally from cruise ship business, where we do all sort of waste water and waste management on board cruise ships. So a lot on wastewater treatment and waste management, food waste handling, and so on. And we just celebrated that we had put 100 wastewater treatment plants on cruise ships last week, so that was nice. We have a very good market share on this. And we have developed pyrolysis for the cruise ship in order to valorize the organic waste on board the ships, which I come back to. Last years, we have expanded quite heavily into land-based activities on pyrolysis and biochar, and have bought ETIA, the French technology company, which holds the biogreen pyrolysis, which was the technology Gerhard used in his biochar testing. And most recently, we also bought C.H. Evensen, a Norwegian company, which is long history in high temperature applications and ovens. The company is 250 happy people working for improving the environment. We have some, last year, I think we will be over 70 million euros in revenues, and we have a good 200 million euros in order backlog for the next years to come. So it's safe and sound. We also have a spin-off, which is called WOW Green Metals, which is a company that now will put up larger facilities for biochar from waste wood for the metallurgical industry. We have developed a microwave-assisted pyrolysis system for cruise ships. It was installed this year. We are doing commissioning this year, and it will go out sailing in the autumn, handling waste, water, sludge, and food waste from 10,000 people on board the ship. So you could see the reactor where we have the microwaves coming in, heating up the sludge coming from top. And then we have a transport screw, activation screw, where we can heat it further up if you like. The gas will come off at the top, and we pull the char out through water bath to keep it safe and sound and for storage in the ship. The wastewater treatment plant has an organic loading typically equal to 50,000 people equivalents. So it's almost a small city worth of sludge and food waste that we are treating there. And we will typically produce a ton of char a day when this is in full operation. This picture is from the same test site as we have done all other tests, and a lot of the emission tests that we have done together with the Norwegian Geotechnical Institute and Gerhard and Erlend is from this plant. The French ETIA company with the BioGreen is a very interesting asset for us, and it has the electric heated pyrolysis reactor. It's a development for many years. It's been heavily used for treatment of spices and food for sterilization. So we have a huge number of installations worldwide on that topic. But it's also extended its operational envelope to do pyrolysis all the way up to 900 degrees. And this is the technology we have used on the chars that Gerhard just talked about. A standard machine would typically handle a ton of biomass per hour and can produce some 200 and 250 kilo of biochar per hour. And then the third technology that we now acquired and developed together with C.H. Evensen is a rotary drum type of reactor. We are now building a new machine. You could see the happy crew here with the drum. So we are building now a new machine that can do a ton of biochar per hour or 5 tons of biomass. And this is a hybrid machine that could go on electricity or on pyrolysis gases. It's also serviced for 900 degrees, so we can really come up to temperatures that is relevant for the properties of the char that Gerhard was talking about. 2 weeks ago, I was together with these guys, and I was inside the combustion chamber here. So it's really picking up and is soon to be ready. I'll flip through some few examples of what we are doing on biomass in particular with the BioGreen technology. In Sweden, in Helsingborg, we are putting up a machine now. It's starting up this week, I think, and it will do garden waste, green waste from the municipality and make biochar for the agronomic purposes. And the pyrolysis gases will be burned and produce hot water for domestic heating. If you are lucky to go to Helsingborg the 15th or 14th of June this year to the Biochar Summit there, arranged with the regional or the Nordic Biochar Association and the European Biochar Industry Consortium, then you will have an opportunity to visit this plant. Another exciting example from the BioGreen system is the one in Hamburg, in which there are processing the shells from cocoa beans in a big chocolate factory. So the cocoa bean shells will go for pyrolysis, and then coming from the chocolate factory, and the steam will go back for purpose in the chocolate production. And there we also have a very nice biochar for agronomical purposes. It's exciting char, a lot of alkali, it's a lot of potassium and phosphorus and so on. So it's really a valuable resource to recover. North in Sweden, we use some wood chips in order to make high-grade biocarbon for the metallurgic industry. So here we are talking about 92% fixed carbon, very little volatiles going directly for the steel industry. Another example of waste valorization is from Philip Morris, their tobacco factory in Switzerland, in which we have put in place a machine to handle pallets, cardboard, and also the organic residues from their own production. And the steam is used from the pyrolysis gas to offset natural gas in their heating duties. And in this project, you may see here we really come to terms with our skills in the cruise ship industry, in which we are very used to work in very confined spaces. And we were allotted just a small building for the pyrolysis equipment and the steam production. So we had to fit it in with millimeter precision. Another exciting industrial venture is now we have running a pilot on end-of-life tires, granulated car tires that is pyrolyzed in order to recover carbon black. And we have developed our process to the extent that the carbon black coming out is equivalent to some of the commercially available carbon blacks for this industry. So the client is happy, and we are now developing industrial scale projects on this. You can see we have a rather high yield, the recovery of the carbon black. Then we have some very interesting oils that could be used, and also some gas for energetic purposes. Then for the topic of today, in Japan, we have had a pilot for some time, a large pilot, you can see there, doing sludge from wastewater, dried sludge pyrolysis at more moderate temperatures. Here the regulations is such that that sludge is prone to be incinerated, and now we make a high energetic biocarbon that or coal that can go to a coal-fired power plant for heat evaluation. And now with this client, we're also looking into developing more full-scale projects in Japan, which is also very interesting. But again, their regulations limits the application of biochar for other purposes. As Gerhard also mentioned, we have a nice testing infrastructure with our innovation lab. We are at the moment in Norway, 16 people. And we have a R&D team in France. So we are very well capable of doing providing this type of biochars, and we connect with all sorts of research programs in order to get these exciting results that we heard about earlier today. So we are very happy with the situation with the Norwegian Geotechnical Institute. We have had a lot of exciting long nights running the tests together and measuring campaigns and so on. So this has been very successful, I think. Here you can see Gudny Flatabø. She is our PhD student now running her PhD project on the integration of anaerobic digestion and beneficial use of the pyrolysis gases and condensates. That is, we try to make the pyrolysis gases and condensates biologically converted to methane, which I think is a very good combo if you are looking at doing pyrolysis of digested sewage sludge. And in this test facilities, we could easily then provide a huge number of different biochars, and we are happy to see that a lot of master students take those chars and do their studies and research on this. And last year we had some 5 master students with very nice results. Katinka this is the master thesis that Gerhard was talking about. So also other topics about the elimination of pollutants has been checked in this. So to substrates for anaerobic digestion, which is of course the nice clean substrate you could think of. They are not necessarily that clean, and as Gerhard also told you, there may be a lot of pollutants in this. A traditional wastewater treatment plant would have a standard mechanical treatment and a biological treatment, in which the sludge is normalized, digested in order to reduce volume and also to do some energy recovery. Then it's dewatered, and the biosolids, or the anaerobically digested sludge, is then disposed in many countries still to agriculture or land applications. In Norway, I think we have almost 80%. The same in UK. There is a very practice, but we see this concern about stricter requirements for eliminating these organic pollutants, and we will see that in the future this would not be sustainable. ORF has made a roadmap for US just to illustrate it, what was sort of the history of handling biosolids or sewage sludge from wastewater treatment plants. There was in landfills, it was smelly. They tried to stabilize them with eliminating some pathogens, reducing vector attraction and so on. But then we see a historical trend where these emerging pollutants typically would stop the current practice, and then what to do. And we think that doing biochar, doing pyrolysis of the biosolids, getting valuable products like sorbents, and also use them actively in agricultural applications. There are already a number of countries now putting together some rules and regulations for this. There are a lot of committees and projects working on the future treatment of biosolids. We participate in some committees in the US on the topic, and we are also invited into larger workshops now next week in UK on the same topic. We heard already from Australia that there has been so strict limits that some areas now ban the land application of this. So we think pyrolysis could be a good way to do it, but integration of pyrolysis and anaerobic digestion is delicate and needs to be considered carefully. And this is just an example of the anaerobic digester, typically dewatered to some 25%, I would say, and then it needs to be dried, and then you could do the pyrolysis. You could make some steam out of the pyrolysis gas to run the dryer, and you would get some biochar. So this is a typical setup. The dryer would need a lot of heat to evaporate all the water from this very wet sludge. And in our group, Oda Kjøllaug Svennevik, she made her PhD on thermal dewatering of these type of sludges, and in her PhD she looked into a wide variety of sludges from all over the world, from all sort of origin, and then she compared sort of thermal treated dewatering with non-thermal treated dewatering, and long story short, doing this type of thermal dewatering could almost double the dry solids of the sewage sludge, meaning we could reduce the drying with 50%. So this is an energetically efficient way to handle the sludge, preparing it for pyrolysis. So what we did, was to put in place, we developed this thermal hydrolysis system that could handle the sludge. And what you see in this slide is actually the wastewater treatment plant of the Oslo airport, the same sludge as Gerard referred to. So when you remember the picture from the firefighting testing in his presentation, that was in the wood just behind this plant. So the sludge, we tested raw sludge, not digested, but raw sludge in this case. And we could run it through our thermal treatment system. It's inside here, and this is the same we do now on cruise ships. So this is just a full-scale version inside this container, handling some 4 tons of dry solids per day. And on top here we have some steam boiler, and we have a centrifuge that just drizzle down the 50% dry solids sludge. And this is you can see the picture here. This is easy to dry, and we have a decent scent rate that would go back to the wastewater. So this is further dried in our dryer at the test facility, and then we have pyrolyzed it, and then Gerard and his colleagues has made all the nice analysis of it. Another way to do it is to take sludge, either raw sludge or digested sludge, but to a central hub, and then do thermal hydrolysis and dewatering. Doing thermal hydrolysis, you could typically hydrolyze up to 30% of the COD, or the energy in the sludge. This is a nice substrate for digestion, easily degradable. And then we do a dryer with a much lower effort, since the sludge is already very dry. And then we can send it to pyrolysis. We can make a steam boiler to run the dryer and also to run the thermal hydrolysis. We could also bring the pyrolysis gases and condensates to the digester. This is the PhD program Gudny is doing now. And we can also take the condensate from the dryer into this type of digester. So we could recover nutrients like nitrogen, and then make biochar. We see a benefit of bringing a combination of sludge and green waste. We enhance the energy balance, since digested sludge could have a very low energy content. Most of the energy in the sludge, or 50% at least, went to biogas. So the remaining is in the sludge. Bringing in some garden waste could increase the carbon content, and may also have some synergetic effects in terms of other properties of the biochar, which we will explore now in the near future. And what about the oils and tars and acids and gases going in here? This is something we are doing tests of as we speak. We do analysis of the liquids. The gases are rather well documented in terms of biological conversion to methane, like hydrogen and CO. So they would be converted if we put them in the right way and in the digester. But the condensates are more tricky, and if we bring these condensates in, typically we would see in a full-scale digester that some 5 to 10% of the original anaerobic digester would the condensate from the pyrolysis of the subsequent digestate would typically contain 5-6% or up to 9-10% of the in-feed COD. So what we have done, we have tried to test the sludge suggested, and also sludge including the condensates from the downstream pyrolysis, and see how they act together. It is a concern. Sorry?
Can we try to wrap up in the next couple of minutes to reserve some
Okay.
time for Q&A?
No problem. I will be quick. So we will see that we could convert a lot of these condensates to methane, which is very interesting. And now we are running the continuous systems for some time, and we are very encouraged by the results now. So the synergetic effects of anaerobic digestion and pyrolysis with microbiology for converting the pyrolysis condensates back to methane is a viable route, which I think makes very much sense. 1 minute just to say that with this, I think when we now know all of these good things about pyrolysis of biosolids, what in sort of the global perspective. And here, sludge effect with Hans-Peter Arp is a nice illustration of this. They have looked into the pollutants and the sludge treatment in Norway in total, very complicated, making all the treatment processes, all the flows, all the mass flows throughout for Norway, and they can follow the sludge for Norway. I think this should be done for any country. They could also follow the same pollutant here, like OPFAS, what happens with them through the system. And then we could start to do some hypothesis, what happens if we are able to do pyrolysis. And then we could significantly reduce the environmental impact on these type of things. So this is also exciting projects to be part of. And I think these type of methodologies should be used widely. So to sum up, we think pyrolysis of sewage sludge biosolids is important for eliminating pollutants. We need to know how to integrate, how to handle the sludges. And we also need to have industrial scale systems that could take the sludge flows from typical wastewater treatment plants, which we now have put in place and are ready to offer. Okay, thanks.
Thank you so much. And Gerard, if you could come on, thank you for answering a lot of the questions in the Q&A section, because I don't think we have too much time. But one thing, Gerard, that, Paul, there was a question about what's the cost comparison of the sewage sludge biochar versus the activated carbon that's currently used or was used in the testing.
Oh, yeah. It will be cheaper for sure, because the feedstock for the sewage sludge biochar is actually with a gate fee. I mean, the wastewater treatment plant pays to get rid of it to the extent of some $150 per ton of 25% dry solids. So they pay a lot for water. So you have a nice gate fee, and the processing cost is not that bad. So I would say it is a very attractive business case compared to activated carbon.
Yeah, Gerard, did you want to add anything on the efficacy or, the ability to regenerate, how many times you could do that or any of that?
About this regeneration, we haven't looked at that yet, but yeah, there's of course no doubt that if you use a starting material with a negative value and you don't have to transport it half the way around, it's both economically attractive, but also ecologically the carbon footprint was way lower than if you have conventional activated carbon from lignite coal from often very dirty mines in East Asia. or you have it from coconut shells. That's then kind of commercial activated biochar, but you still need to transport it. And these coconut shells, yeah, you can use for other purposes too. So the key is to have this worthless material, and then also yeah, cleaning it up in the way. But we will do a life cycle analysis comparing common practice to yeah, treating sewage sludge in this manner.
Have you done any research on, what the methane impact might be of pyrolyzing the sludge versus some of the other current practices?
No, we haven't looked at that, but yeah, might be a positive factor as well. I know that for rice husk, the biggest factor, a positive factor in LCA of rice husk biochar is avoided methane emissions from piles of rice husk lying around and rotting.
Same with the, I mean, sewage sludge has been a concern not only for that, but also for laughter gas emissions. So we take part now in a project where we look at special micro or bacteria that could be suppressing the laughter gases. So we combine biochar and some compost with this and add those special bacteria to try to hold back or reduce or eliminate the laughter gas as well.
Hydrogen sulfide?
No, N2O.
N2O.
Okay. I know there were several questions about the activation process, and I think you answered some of them, but maybe you just want to spend a minute or two talking about that.
Yeah, I think I should address both the activation and the binding mechanism of the PFAS to the biochar, because there was a lot of questions about that, and it's better to explain it orally. Let's first take the activation. It was steam activated. You can do physical activation both with steam, so the H2O water, and with CO2. What happens is that part of the carbon in your biochar matrix reacts with the water to hydrogen gas and carbon monoxide, and then disappears as a gas. With the CO2, it's C plus CO2 gives 2CO, which also disappears with the syngas. The result of both is that you extend your pore system and you clean the surfaces of your pores. So if you activate, you get both a higher capacity because you have more pores where the PFAS can be accommodated, and you have cleaner pore surfaces where they can be nicely bound. 100% activation is that you add so much water vapor that if every water molecule reacts with every carbon molecule in the biochar, that you have no biochar left. But this reaction, of course, is incomplete. So yeah, usually about 40–50% will actually react, and then you react actually half of your carbon, but you get a very nice extension of your pore system. So yeah, you get a much higher sorption capacity because of that. Yeah, I now realize I should have explained the sorption mechanism before the activation, because you need it in the explanation. But the mechanism is that especially these tails, these hydrophobic tails of the PFAS, so these C8, F10 tails, they interact very beneficially with the aromatic carbon surfaces in these narrow biochar pores. So these PFAS molecules really get stuck in these pores. And this interaction is so strong that it's very difficult to get them out again. The diffusion through the pores is very retarded anyway, because they only just fit through. I won't go too deep into sorption theory, but if the sorption coefficient is 1,000,000, the rate out will be 1,000,000 times lower than the rate in anyway. And also, if you put biochar in soil, it will slowly get baked into soil aggregates, and yeah, you get kind of organic matter coatings on the surface of the biochar, which even hampers the release of the PFAS more. So if you bind the PFAS in biochar, it's basically virtually getting stuck there. Very little will be released also over time.
Mhm.
Because of this mechanism.
There was a question about contact time required for removal, and they thought in your charts it was 30 days, but most systems measure contact time in minutes to hours. Have you done any real world simulations of these time frames?
We will do that for air cleaning. We will actually do very fast tests where there's only a matter of seconds or less contact time. But theoretically, we wanted to publish this work, so you don't want any fuss with reviewers that maybe equilibrium was not reached. But again, sorption theory dictates that the rate coefficient in is about 1 million times faster than the rate coefficient out. Theoretically, I can tell you that we use 14 days equilibrium time, but the first 70 to 80% absorption takes place in 5 minutes, and then the rest is slowly converging to that equilibrium. But we just want to be sure that there's equilibrium, and we don't want any discussions with reviewers of our papers. But actually, the adsorption, so that the take up, it goes really fast. In water and air systems. In soil, it's a little bit different because you need this mass transfer from the soil particles to the biochar. But since these compounds are relatively water soluble and not bound so strongly to the soil particles, also that is relatively quick. That's why we only needed short contact times also in these soil columns with biochar.
Mm-hmm.
So relatively benign compounds in that sense. It's relatively easy to mitigate if your sorbent is strong enough.
Well, we have to wind up a little bit, but I can't believe nobody asked this question, Paul. When is the first cruise with a microwave pyrolysis open to the public?
It's already they have already taken orders, so it's fully booked for the first year, I think, the ship. So you have to be patient, but it will go out sailing later this year, and I think the first passengers come along early next year.
All right, we'll have to keep that on our radar.
Absolutely. And when we looked at the ability or the availability of tickets, it was already sold out for 24 and sometime in 25, I think.
That's impressive.
So people are interested in pyrolysis for sure.
Yes. There was a question about whether we will share the questions and answered, and there were a number of unanswered questions that we didn't get to. I think we have that capability, and if we do, we will definitely share them with folks, and we may come back to Gerard and Paul for some that we just didn't have time to answer. But sure. I want to thank you both for putting together this presentation. I think it was really informative. I think there's a lot of opportunity here. So yeah, thank you so much. Mm-hmm. I'm going to share one slide, I think, if I can figure this out, about what's coming up for IBI. If any of you, and I know Paul, at least you are coming to the event in France early next month, we will be there as well. And anybody else, if you're going and would like to meet up with either Wendy Lou or I, just give us an email or just send us a note. Sorry, I'm multitasking here. Next month's webinar is already planned for February 16th. It'll be on permanence. Samuel Ambiven, I think I'm pronouncing that right, and Hans-Peter Schmidt will be talking about that. Wendy Lou and I will be attending the Aspen Institute Climate event down in Miami, Florida. So we'd love to meet anyone in that part of the world. And then finally, I just wanted to say that we are hosting the very first IBI Biochar Academy at the end of June in my hometown of Canandaigua, New York. We'll have we're hoping to bring about 40 people to that event. We are looking for scholarships for up to 10 attendees, and the application period is open from now until the end of February. So if you have any questions about that, please reach out. But with that, I will say thanks again. We really appreciate your presentation and all the work you've done on this research. Thank you.
Thank you so much for having us.
Yeah, thanks very much.
Take
Tusen
care.
hjertelig takk. Bye-bye.
Ha det bra.
Bye. Krista, I'll let you shut things down.
Thank you again to all the panelists and for all of the attendees joining today. We really appreciate you taking the time out of your day to do this. And I will be concluding the recording now. I hope that you all enjoy a beautiful weekend.
Thank you.